Howdy folks! Okay, so the long-awaited pre-lab for decomposition of hydrogen peroxide. It's the second lab in our lab series that deals with kinetics. And kinetics is the speed of reactions. This sort of some intro stuff that I had in the other video, just in case you probably have seen that video before, so I just had this pre-written on here. Why study kinetics? And I probably mentioned this in the other video, I don't really remember. But when I first learned about this stuff, I was always like, gosh, why there's such an emphasis on kinetics? Kinetics is the speed of reactions. It says up there. Why is it such an emphasis? Just be patient, wait for the reaction to happen. It turns out kinetics and the speed of reactions affects a lot more than just how long is this reaction going to take us, because we've got to be someplace. A lot of the time there may be processes that you want to happen and processes that you don't want to happen. And the way that you can favor, or the way that you're going to get the one that you want to happen, is if the kinetics for that reaction are faster than the kinetics for the undesirable one. They can help you understand and appreciate the mechanism of a reaction. We talk about mechanisms a little bit here and there, but you start out with some reagents, you get a product, but how are those bonds broken, and then how are new bonds formed to get those products? That's the mechanism, and kinetics a lot of the time can give us important information that helps us figure out what is the mechanism, how is that happening. And kinetics can also, sort of along with mechanism, can help us optimize a reaction. Maybe we're not getting a very good yield in our reaction, and we'd like to get a better yield, so having appreciation of the kinetics at play can help us do that. Okay, so I always like to sometimes find, I think students get a little bit confused in the different ways that we talk about reaction rates when we hit this subject. So in general, I like to point out that there are sort of three different types of ways of describing rates of reactions that we deal with usually in the lecture course. There's other ways of talking about rates and stuff, but three primary types of rate equations that we deal with. And the first are relative rates. And relative rates simply tell us, if we know the rate of one reagent, how fast is it going away, and we know the balanced equation, we can relate that rate to the rate of some other part of the reaction, like a product. So if we know the rate at which this is disappearing, that can give us information. We can relate that to the rate at which some product is appearing. Okay? And relative rate equations, they don't tell us absolute rates, okay? They just tell us relative rates. So it could be, it could tell us that this product is appearing twice as fast as this one is disappearing, okay? But it doesn't tell us, how fast are either of those things happening. It could be very, very, very slow. We just know it's happening at twice. Or it could be very, very fast. So that's relative rate equations. And we're going to use those, we're going to use the general principle of relative rate equations in this lab. We don't use it really directly, but we're going to use it indirectly. The other is known as a rate law. And that's actually sort of the point of this laboratory exercise, is to determine the rate law for our specific reaction. And a rate law tells us what is the rate of reaction, okay, with a certain amount of starting materials left over, okay? Your rate depends on how many starting materials. If you think we often talk about the collision model. Reactions happen because molecules collide with each other, okay? So in general, the lower the concentration of those reagents, the fewer collisions there are, and the slower the reaction is going to be, okay? So a rate law tells us what is the rate given that current concentration of the reagents. Okay, that's a general definition. A lot of details in there, and I'll go into those details. And then we have integrated rate laws, which we're not going to use in this laboratory exercise. We use that in the reaction rates of everyday processes lab, if you've already done that one. But integrated rate laws tell us how much of a certain starting material is left given a certain amount of time that has passed, okay? So don't confuse integrated rate laws with rate laws, okay? All right, so let me put some of that stuff on the board real quick. Okay. Okay, so our intro subject, rates. Three different types, equations, discuss. Okay. One is relative rate equations. Okay. If we know the rate of one reagent, okay, or one product, okay, in a reaction, all right, these equations relate the rate to another reagent or product. I think the analogy I like to use in lecture a lot is making a bologna sandwich. Okay, let's pretend you put one slice of bologna with 2 pieces of bread. You know that the relative rate of consumption of bread is going to be twice that of bologna because it takes 2 pieces of bread for every 1 piece of bologna. Again, that doesn't tell you anything about how fast those bologna sandwiches are going to get made. Depends on the chef. All right. 2 rate laws. The main subject of today's experiment. I use that word a lot, or those words a lot, so I'm going to abbreviate those RL from now on. Tells the rate of reaction given how much reagents are present or left. You know, could be at the very beginning that you're talking about, or it could be after the reaction's gone for a while. Okay. And then that third type, integrated rate laws. Okay. Tells how much reagent after time t. Okay. Okay. Yeah, and we use that one, if I didn't mention that, we use that one in the other lab where the reaction rates of everyday processes. Okay. So how do we determine rate laws? We determine rate laws using a technique, or one of the ways you can determine it is using initial rates, okay? There may be many different reagents that you put in there to start a reaction, and they can have different effects on the rate of reaction. Okay, just like my bologna example, bread has a different effect on the rate of sandwich making. Okay, you can also have things that you add that they have to be there in order for the reaction to happen at all, but they may not actually affect the rate of reaction. The rate of reaction may be independent of the concentration of that. I'm probably beating this analogy to death, but let's say the knife that you're using to spread the mayonnaise on your sandwich or whatever, you know, having more knives around isn't necessarily going to affect the rate of reaction, but you need a knife to make it happen. Should leave it alone now. Okay, so let's take a look at a generic reaction. If you by chance have had me for the lecture portion of this course, then some of my notes here are somewhat similar, but not total duplicates. Okay. So the way that we're going to determine the rate laws is by a process called initial rates. I'll explain that a little bit better, why that term initial rates here in a second. But for now, let's just call it that. So determining RL rate laws with initial rates. Okay. So just real general sense. Also, I've used this before, I believe, in this particular course, but a delta sign I use as a symbol to change, or changing, as we have here, just to make it a little faster. So, changing different reagent concentrate. That's my symbol for concentrations. I don't have to write out that whole word. Okay. Changing different reagent concentrations can change rate. Okay. All right. Okay, so a reactions rate law. All right, let's draw our generic reaction. Okay, it's going to be A plus B. Gives us C and D. So not real atom symbols. Okay, these are the coefficients, like if it takes 2 A's for every 1 B. Okay, stoichiometry of your balanced equation. It's going to go to little c of reagent C plus little d of reagent D. Okay, so reagents product. All right. We can give what I like to call a general rate law. Okay. At this point, without any data, we can figure out the general rate law because we know the reagents that you got to put in there. Okay. We need to do the specific rate law needs to be determined experimentally. That's what you guys do. Okay. So general rate law for this reaction, okay, is going to be rate equals rate constant, okay, times the concentration of A, okay, and that's going to be raised to the m power, okay, concentration of B. We just list the different reagents, okay, and then raise it to power of m and n. Okay. There are other situations, for instance, when we deal with equilibrium and equilibrium constants and stuff, where these powers, okay, when we're setting up like an equilibrium constant, we do a very similar type of form, and these exponents are actually the coefficients here, okay? But for a rate law, if we don't know anything more about the reaction, for a rate law, they are not necessarily. They may be these coefficients, but not necessarily. So we leave them open, and then we have to look at experimental data in order to figure out what is m and n. And in reality, the whole point of this lab is to figure out m and n, and in fact k. All right. Rate constant. So that's rate constant. Rate constant sort of encapsulates if you have a low rate constant, then a lot of the collisions will provide you enough energy to climb that energy of activation hill to give you a reaction. Okay? You have a high, I'm sorry, I said it the absolute reverse, apologize. If you have a high rate constant, then most of the collisions will make the process happen. If you have a low rate constant, then a lot of those collisions don't have enough energy in order to make the reaction happen. They don't have enough energy to climb the energy of activation hill. Okay? All right. You may wonder, oh, you made this general rate law just taking all the reagents and putting them here in the rate law, but didn't you say that maybe some of the reagents that you put in the flask don't have any effect on the rate? Well, yeah, that's absolutely true. You can still have a general rate law like this, but if that's the case, then you're going to find that the exponent for that particular reagent, if it doesn't affect the rate, the exponent is 0. What's anything raised to the 0? 1. So this whole term would just become 1 because it doesn't affect the rate. Okay. Oh, okay. Okay, so the general idea for initial rates to figure out those exponents is you can run reactions, have certain concentrations of, say, A and B, run the reaction and see what the rate is. Let's just take for granted right now, you have some way of monitoring what the rate is. Okay, we'll talk today how we monitor the rate for the reaction that we're doing. But you have some way of monitoring the rate. Okay, so you put in a certain concentration of your A, your B, and see what the rate is. All right, and then you hold one of them constant. You don't want to change both of them at the same time. You haven't learned anything. Hold one of them constant to how you did it the first time, but then change the other one. Say you double it. Okay, and if you double that reagent, okay, and let's say it doubles the rate, then you know algebraically, I wish I could get the formula up there, Yeah, maybe I'll put it back up here in a second. But algebraically, you know that the exponent has to be 1, okay? Because doubling this, the only effect it had was to double the rate. That necessarily, the exponent has to be 1 by algebra. Okay, an exponent of 1 is the only thing that could explain that. By doubling the concentration of one of them, it doubles the rate. Okay. Now, what does it mean if we double the concentration of A and it quadruples the rate? That means, again, algebraically, the only way that could work is that the exponent for A is 2. Okay? Doubling that, you multiply it by itself, quadrupling the rate. Okay? And like I mentioned before, let's say you change A, you double the concentration A, and it has no effect on the reaction rate. Then A doesn't affect the rate. The concentration of A doesn't affect the rate. Still may need to be, you need some A in there to make the reaction happen, but it doesn't matter how much you have in there, it's not going to change the rate. Okay, so rewrote my the general rate law on the board. And put some notes with what I was talking about doubling and what it does to the rate and all that good stuff. So, I already said this, but reagents can affect reaction rate to different degrees. Okay. M and N, the exponents of your individual reagents, are sometimes referred to as the order, okay, with respect to that particular reagent, with respect to WRT, and have to be determined experimentally. And so, I think this is just how I described it. Let's put it on the board. So we're trying to determine M here, yeah? The general idea of how you go about this process. Okay. Change concentrations of a reagent while keeping the others constant. If you're changing multiple things at one time and it changes the rate, you don't know which change had the effect. Okay. And then C, the effect on quote-unquote initial rates. Again, I haven't explained why we're calling it initial rates, but I will in a minute. That's the rate right after the reaction starts. Okay, so commence the reaction, then we check the rate somehow quickly, and I'll explain why. Why do we need to do it quickly? Okay. Now, maybe you double A, okay, and as a consequence, the rate doubles. Okay. So M must equal 1. Okay. Again, I hope it's pretty evident algebraically. If we're trying to figure this out and we double whatever number this is, I mean, just pick any number. Let's say this is 2, okay, and our rate is 10. No units, no nothing. This is 2 and our rate is 10. If we double this to 4 and then this also doubles, the only way that makes sense is if m is 1, okay? Because its effect is I'm not going to explain it anymore. And there are ways you can like prove this and so forth and so on. I'm hoping it's more of an intuitive, that you can see it intuitively. If you look at the procedure for this lab, the written procedure that you read, all that really complex symbolism at the beginning of that procedure is that type of proof of showing that kind of thing. In any case, hopefully you see it. All right, and well, let's say maybe, what if you doubled A, okay, and the rate quadruples? Okay, the only way that could happen is if m equals 2. Okay? Doubling this doesn't just double that, it has a greater effect. Okay, it quadruples that, and it does that because that is 2. All right? Okay. And then just like I said a minute ago, what if you doubled A? Okay, and the rate unchanged. Okay. Therefore, m is 0. Okay. Last situation, i.e. rate isn't affected concentration of A. Okay? Not part of the rate law. Okay? All right. Let's look at an example real quick. Okay. I'm going to stick with A and B, not actual reagents. We'll discuss our reaction today of potassium iodide and hydrogen peroxide in a second. But for now, I'm going to stick with I and just give you some actual values to hopefully make this a little bit more clear. Okay. All right. Let's call this experiment 1. Okay. Shoot. Okay. Use the word experiment two different ways here. So switching to trial, which is how our lab does it. So that's a better way anyway. So trial number. Okay. And then concentration of A in molarity. Brackets usually means molarity anyway, so it's kind of redundant, but let's just make sure you're clear on that. Again, in molarity, and then initial rate. Okay, and our rate is going to be molar per second. And we'll talk about, actually not even in this one, you know, again, what are we monitoring? How are we describing the rate? Okay, you could describe the rate by the appearance of C, or the appearance of D, or the disappearance of A. Okay? But for our information here, to understand this example here, we don't even need to define how we're monitoring the rate. Okay. All right, so for trial 1, all right, concentration 0.100 molar, okay? Concentration of B is 0.100 molar. And here's our initial rate, 4.0 times 10 to the negative 5 molar per second. Molar per second is moles per liter per second. Okay. And then in trial 2, okay, here's our concentrations. I'm going to just put this in here, and then I want you to think for a moment on what we can conclude about M and N. Okay. All right, and then in trial 2, this is the rate that we observed. Okay. And then in trial 3. Don't need these M's if it's up there. All right, and here's our rate. Okay. All right. So given that data, what could we conclude about M and N? Think about it for a minute. Thinking about it? Okay. Well, so if you look, what change do we make? This is sort of our initial state. In all of these, if you have 2 reagents, then you need at least 3 trials, just like we have here. And you're going to find that is the case for the experiment we do today. So we can look at this as sort of our initial state, trial 1. And then going to trial 2, what did we change? Well, we doubled the concentration of B, okay, and kept A the same. And what was the effect on the rate? No effect on the rate. What does that imply? That implies that N is 0. The concentration of B has no effect on the rate. Okay. And in trial 3, we keep things constant for B in terms of its concentration, but we double A. Okay. And then what was the effect? Did it double the rate? No, it quadrupled the rate. Okay. That indicates that M must be 2. Okay. All right. Let me put some notes up there for that. Space here. If you're a little bit unclear on how if it's not intuitive that quadrupling the rate means that the exponent must be 2, or doubling it means that the exponent must be 1, then I can point you actually to where I do an entire lecture on this stuff for the lecture course, and I can point you to that video. So let me know if that's a problem. Actually, I might add it to the end of. I might add a link to the end of this video. That's a better idea. Okay, just so I've said it here now a couple times, but notes are complete. Going from this one here, we doubled concentration of B, okay, with concentration of A constant, okay, and no change to rate, okay. Therefore, international symbol for therefore, three periods, B not in the rate law, not in the specific rate law, okay? All right, what change did we make? We doubled concentration of A. Okay. Holding concentration of B constant. Okay. And the rate quadrupled. Okay. Therefore, n equals 2. Okay, so we can now write our specific rate law. Therefore, the specific and general rate law, I think those are my terms, so just so you're aware. Specific rate law, rate equals the rate constant times whatever the concentration is of A squared. No B term. Okay? All right, now we can actually determine K. How can we determine K? Well, rearrange the equation, solve for K, and then take any one of these trials and you have all your variables. You have your concentration of A and you have the associated rate. Okay? Good. Determine. Okay. Using data from any of the trials. Okay. Plug into the rearranged formula. Rearranged formula for here would be K equals the rate. Okay. If you had a different rate law, specific rate law for your particular reaction, then the form of this one when you solve for K would be a little bit different too. All right. So I'm going to talk now about the specific reaction that we're doing, which is the decomposition of hydrogen peroxide in the presence of potassium iodide. Okay, so today, determining rate law for reaction of hydrogen peroxide with potassium iodide. Okay. We're going to see that this is actually a two-step reaction. Okay, so you put in hydrogen peroxide, you put in potassium iodide. The iodide is actually consumed in the first step. But then it is recreated in the second step. So you can derive an overall reaction, sort of like a net ionic equation, where you cancel out the things on both sides, right? And you see that iodide isn't actually even in the overall reaction because it's consumed but then regenerated. In a sense, it's just a catalyst. That doesn't mean that it doesn't affect the reaction rate necessarily. Catalysts can be very important to reaction rates. Okay, so it's two-step, and as we're going to see, the first step is actually the slower of the two. Okay, and anytime you have multiple steps in a reaction process and one of them is slower than the other, that we call that the rate determining step. Okay. The overall reaction can't go any faster than how fast that slowest step is going. And in all kinds of analogies, any sort of assembly line you have, if you have an assembly line of people doing some task, building a rope, building a car or whatever, and there's one person that's particularly slow in this assembly line, the whole assembly line's rate is going to be determined by that slowest person. Okay? And so we can actually develop a general rate law for that slow step, okay? And that general rate law and the specific rate law, once we figure it out, for that slow step is actually going to be the rate law for the overall reaction process, okay? Because the second step is so quick. It doesn't affect the rate. Okay? All right. Reaction happens in 2 steps. Okay. All right. Hydrogen peroxide plus 2 iodide. You may wonder, by the way, all my coefficients here are going to be 2. You may be like, wow, that's not the simplest balance equation. You could just take away all those coefficients if they're all 2. But by making them all 2, that's how it cancels out and shows you the overall reaction. Okay. 2 periodites. Okay. 2 waters. All right. So I'm going to call this equation 1, okay? And we have equation 2 and equation 3, which is, and as we're going to see, this is the slow step, this is the fast step, and this is the overall reaction. Okay? Second step, 2 periodites. Give you, reproduce your iodide, and give you oxygen gas. Okay. Remember, you can add up reactions to get your overall reaction, so anything on the product side of one that's the same as the reagent side of the other, cancel out actually. Okay. And then reagent side of the first one, product side of the second one, so they cancel out. Okay? And that's what gives you your overall reaction. Okay? Overall, 2 hydrogen peroxides are decomposed into 2 water molecules, okay, plus 1 oxygen gas. Okay. That little arrow means it bubbles out. It's going to be critical to our setup today. Okay. The stoichiometry of the overall part of the reaction is going to be important because we're going to draw conclusions about the concentration of peroxide based on how much oxygen we observe. Okay. So we need to appreciate that stoichiometry. Okay. All right. As I said, the rate of overall reaction determined by the slow step. Okay. Another way of saying that is that it is the rate determining step. Okay. All right. So at this point, we can generate our general rate law. Okay, which would be the 2 ingredients that we put in the first place. Okay, hydrogen peroxide and iodide. All right, we'll give them variable exponents. Okay, put in a variable k. All right. So, general rate law, rate is K times the concentration of hydrogen peroxide raised to the n power times the concentration of potassium iodide raised to the n power. Okay? Now we want to figure out n and n just the way we did in our example a moment ago. All right. Okay. So to determine specific rate law, we need M, N, and K. All right. Note, by the way, K changes with temperature. Okay, right? If there's a certain amount of energy that these collisions take, okay, K gives you an idea of how fast those collisions are happening, okay? And the more energy you have, the more you heat that up, K is going to increase because you're getting more and more collisions, okay? But for this, so if we're trying to determine M and N for our specific rate law, all those reactions have to be done at the same temperature. Okay, and you're going to see that we do at room temperature to figure out our specific rate law. Okay. All right. So before we go on, I want to how are we going to monitor this reaction? I want to draw the setup, artist's rendition of the setup, and show you how we're going to do it. So, voila. Okay. There's my best effort. So this is where the reaction is going to happen. Okay, we've got an Erlenmeyer flask, and the Erlenmeyer flask is sealed. Okay, a little glass tube in there, and then some rubber tubing that comes along to the top of a burette. Remember, a burette is something that we can sort of read the specific volumes of water. Okay. And then the burette is actually connected on the bottom with another rubber tube up to, I forget the terminology that we use for this bulb. I think a pressure equalizing bulb. Hopefully that's what we call it. That's what I'm going to call it right now. And then this is all filled up with water. Okay? When you're setting up this reaction, the pressures are going to be equal, and the height of these, the two water levels will be equal. Okay? And then you're going to add a certain, so the concentrations that you start with are all the same. We're starting with 0.10 molar potassium iodide, 0.88 molar hydrogen peroxide, and then we're also adding a little water. Okay? And so we're going to add those into here, all right? And they will react, okay? We know from looking at the overall reaction, all right, that oxygen will be produced, okay? Now, we're going to end up describing the rate of reaction by describing the disappearance of hydrogen peroxide, okay? In part, that's just convenient because we can describe it as a molarity, okay? But we don't have any way. We can't look in there. It's not visible. We can't use UV light. And there's no way to monitor directly how the concentration of potassium, of hydrogen peroxide is dropping. It is dropping, right? We know that over time its concentration will drop because it's being turned into oxygen and water, all right? So we want to be able to describe how it's changing, but we need some way to monitor it. Well, we're going to monitor it indirectly, okay? We're going to monitor it through the carefully seeing how much oxygen we create. Okay, and then using the stoichiometry of that equation to decide, well, how much in a given time interval, how much hydrogen peroxide was consumed. Okay. We won't describe the rate specifically with oxygen, with the concentration of oxygen, because it's not in solution. Okay, it's bubbling out into the air, and so it doesn't make it very convenient for describing the rate. All right. So how are we going to figure out in a specific time interval how much? Well, let me backtrack. It's going to be important that we first know what is the starting concentration of hydrogen peroxide. It's not going to be 0.88, okay, even before the reaction occurs, because it's getting diluted a little bit, right? You're using a specific volume of this solution of hydrogen peroxide, okay, so you can figure out the moles, okay, at some point I think we use 10 mils, I forget now actually, but if we use 10 milliliters, that's 0.01 liters, yeah, you can figure out how many moles of hydrogen peroxide you have, okay, and then you need to figure out how many liters of total solution. Well, you need to count up that 0.01 liter that you used here, and you need to count up how many liters of this did we use, and then how many liters of water did we use, okay? We're going to see that that actually always ends up being 60 milliliters, otherwise known as 0.060 liters, okay? So to figure out our initial concentration of hydrogen peroxide, we simply got to take the volume that we added times the molarity, and that'll give us the moles of hydrogen peroxide, and then divide it by that 0.060 liters. Okay? That'll give us our starting concentration of hydrogen peroxide. All right. Then let's say 30 seconds goes by, and I'm going to chart this out in a second for you. But let's say 30 seconds go by, and we know that some of those moles, some of those molecules of hydrogen peroxide have been consumed. Okay. How are we going to figure out how many moles of hydrogen peroxide have been consumed? By determining how many moles of oxygen have been produced. Now, how the heck are we going to do that? It's a very clever setup. I like this experiment a lot. Well, we're going to use, we're turning it into a gas, okay? As the reaction occurs, what color to pick? The oxygen produced in here, O2's bubbling, O2's bubbling, it's bubbling through here, and it will displace some of this water up into this bulb, okay? Okay, and so we'll call this the displaced volume of water, okay? All right, now, if we know the volume of water that got displaced, we know the volume of oxygen that was produced, okay? If we know the volume of oxygen, okay, and we know the pressure of oxygen, well, how are we going to know the pressure? Well, because the pressure, as long as we keep that bulb at the same height, that's the whole point of this, okay, then the pressure in here equals atmospheric pressure. If it was greater, it would continue to push over into the equalizing bulb. So after it displaces, the pressure is re-equilibrated with atmospheric pressure. So we know the volume of oxygen created, okay, by measuring this little change on our burette. It's got little, it's in milliliters, okay, which we'll need to convert to liters, all right. We know the volume of we know the volume of oxygen that was created. We know the pressure that it's at. Okay, it's at atmospheric pressure. We know the temperature. We're going to use the temperature of the reaction flask. That's probably the best estimation for what temperature the gas is at. Okay, so we use the reaction temperature. So we know pressure, we know volume when that is placed, we know temperature, okay? If we know those three things and we know our gas constant, which we know, then we can figure out the moles. That's the beauty of the ideal gas law. So we'll know the moles of oxygen produced in that particular 30-second interval. If we know the moles of oxygen produced in that little 30-second interval, using that overall equation that I had here a little while ago, we can figure out the moles of hydrogen peroxide that was consumed. Okay? And then we'll know our new concentration. All we have to do is take our original moles of hydrogen peroxide that was in there, minus the moles of hydrogen peroxide that was consumed, and then we have our new moles. The volume in here never changes, it's always 0.06 liters, okay? And so we have our new concentration, all right? And we can do that for every 30-second interval. So as the concentration of hydrogen peroxide drops, we can collect that. Now, if that ends up being linear, let me, okay, so, yeah, so, if that data ends up being linear, okay, and we know the equation of that line, all right, the rate of reaction, the rate of change in hydrogen peroxide consumption, which we define, that's the rate of our reaction, is going to be the slope of that line. Okay? And so we'll do 3 trials that way, changing the starting concentration, just like we did in our example, the changing concentration of these guys, and we'll see what the change is in our reaction rate. Okay, let me put some more details on the board because I'm just chatting here. All right, so in the lab, we do 3 trials. All at room temp. Okay. Changing hydrogen peroxide concentration. Okay, or potassium iodide concentration. All right. Just need rate, okay, for each trial. Okay, just like we did in experiment 1. All right. Okay, and as I've been saying, we are going to express our rate by the change in concentration of hydrogen peroxide. Okay, change over change in time. Okay. Our units is molar per second, otherwise known as moles per liter per second. Okay, that's the same thing as molar per second. Okay. All right, so let's take a look at what example data might look like. Okay. All right, so. Okay, so here's here's an example graph, okay? So we are going to describe the rate as the change in hydrogen peroxide concentration, okay? If this data ends up being linear, okay? The change in that line is slope, right? The change in concentration over the change in time is the slope of that line. Okay? So, if data linear, okay, change, change in hydrogen peroxide over the change in time, okay, which is our defined way of describing the rate of this reaction, is the slope of the line. Okay? So you can do a best fit line as long as it's linear, and then you can add trend line and add that equation, and there is your, and then you can read your slope. Okay? A lot of time when you do that in Excel, by the way, before I forget about it, it should be in your worksheet mentioned there, but a lot of the time when you have it generate a line, it gives you one significant figure. Okay? And you should be able to get at least two significant figures. And there's different ways you can do that on that equation, and I describe it in the worksheet, or you can Google it, so forth and so on. But you want at least two significant figures in your slope, which is your rate. Okay? All right, so we have this line and the equation, we have the rate for that particular trial. Okay, so all we need to do is to be able to get this data of, at 30 seconds, what was the concentration of hydrogen peroxide? At 60 seconds, what was the concentration of hydrogen peroxide? 90 seconds, what was the concentration of hydrogen peroxide? And that setup is how we're going to be doing that. Okay. All right, but I do have a sort of described in words exactly how what I described verbally, exactly how we get those different concentrations of hydrogen peroxide over our 30-second intervals. Okay. Something I do want to note is that often, if you collect this concentration data over the time span of a reaction, it's not linear as over the course of the entire reaction. So reactions often slow down, okay? Because the collisions, there's less and less starting materials, those concentrations have gone down, the collisions are happening less and less frequently. Okay? Then this type of task, if you were going to describe it over the entire length of a reaction, becomes a lot more challenging. Then you need to figure out some mathematical equation to describe your curved line of your concentrations. Okay? And then your rate at any particular time would be the tangent, all that stuff. But a lot of the time, even if the reaction isn't linear, the concentration doesn't change linearly over the course of a reaction, even those reactions are usually linear in the beginning. So if we just pay attention to the beginning and see what that rate is, okay, and see what those beginning rates, how they change by changing the concentrations of our starting material, we can figure out our rate law, which is the whole. We don't need to look at the entire reaction span. If we just look at that initial part, and that, folks, is why it's called the approach of initial rates, okay, because we know it's going to change ultimately. Oh, okay, I think I include that here. Okay. Yeah, write that in your notes just for fun. Note. Change in concentration of reagent, whatever it is, often isn't linear throughout the entire reaction. Okay? Reactions often slow down. There may be some, I can't off the top of my head, I've heard of a reaction that speeds up as it goes on. Yeah, I don't know. I can't think of a reaction that speeds up as it goes on, of reactions that stay at the same temperature. If it heats up for some reason, sometimes reactions can heat themselves up, then yeah, maybe it could speed up, but anyway. So, not linear, but usually linear Okay, so. Let's sort of big picture here. So, need the new molarity oops. That's what I'm trying to do. Put in parentheses. Molarity of hydrogen peroxide. Okay. After every 30-second interval. Okay. All right, well, to figure that out, we have to first know how much we had initially. Okay. So initially, we got our moles of hydrogen peroxide over our liters of solution. Okay. Where are we going to get all those things? Okay, well, we're going to get that guy from the molarity of bottle, okay, times liters used. Okay, again, I don't remember off the top of my head. I think it's like 0.01 liters. Yeah, I don't remember. I think it's 0.01 liters and 0.02 liters for the hydrogen peroxide, and I think the potassium iodide is 0.015 and 0.030, but not sure. Anyway, however many liters we pour in there to initiate the reaction, times the molarity on the bottle, which is 0.88 molar. Okay, and then this, gotta remember to add up the total liters of all three things you're putting in there. Hydrogen peroxide, potassium iodide, water. Okay. Total liters, all three solutions. Which, as I mentioned, is always 0.060. Okay. Now, so what are we going to do? What process are we going to do for each 30-second interval? Okay, and the worksheet I presently have really takes you through this process step by step by step. First by hand, and then for that first interval, just so you get the idea, and then you want to use Excel to be able to generate the other ones. You don't want to have to do every single one of them by hand. Okay? All right, so for each 30-second interval, okay, working my colors today. We want to know the beginning moles of hydrogen peroxide, okay, for that particular interval, okay, that's going to be changing, minus the consumed moles of hydrogen peroxide, okay, over the liters of solution. Okay. Note that never changes. where are we going to get the moles of hydrogen peroxide consumed during that particular step. Get that. From the moles N of oxygen created. Okay. Also in parentheses, watch stoichiometry from equation 3. Okay? It's not one-to-one. You don't get 1 mole hydrogen peroxide consumed for every mole of oxygen produced. Where are we going to get the moles of oxygen created from? We get that from the ideal gas law. Okay. Will have been rearranged. N of oxygen. Okay. Going to equal R T over P V. Okay. And where are we going to get these things? Now R, get that from the table. Okay, that is 0.0. I always felt you knew you were studying enough in your general chemistry lecture when you know that by heart. Maybe you got to even study more than that. Okay. Anyway, liters times atmosphere. And make sure all the units of everything else we're putting in here follow those units. Mole, K, Kelvin. Okay. That is the temp of reaction in Kelvin. Okay. That is pressure in the lab, okay, in atmosphere. Right, and finally the volume, that's the whole point of that complicated setup, is the volume of oxygen created over interval in liters. Okay? Not too bad, right? Let's see, how many space left? Yeah. Okay, so wanted to put sort of a summary on overall what you're going to be doing. Okay. Overall. Okay. Do process for each trial. part of that is going to be some carefully doing your Excel columns. So that the first column is going to tell you, I forget how I sort of organize it for you in the worksheet. First column, I believe, is going to be the volume of oxygen created, okay? And then simply the initial, the last burette reading minus the next burette reading gives you the volume created in that interval. Okay, once you know the volume, then this next Excel column needs to use the ideal gas law to figure out the moles of oxygen. Once you know the moles of oxygen, you need to figure out the moles of hydrogen peroxide consumed. Stoichiometry, pay attention to that. Once you know the moles of the new moles of hydrogen peroxide, then you need to figure, or the moles of hydrogen peroxide consumed in that interval. Then you need to subtract that from the moles that were left at the end of the last interval. Okay, and then you need to figure out the concentration at the end of that interval. And you need to just sort of copy and paste and do it all the way down the Excel sheet. Okay. All right, so do process for each trial. Get the trend line. Okay. Equation. Slope is the rate. Okay, for each trial. Okay. And then determine the order. Okay, kind of just the way we did in experiment 1. In other words, determine the order with respect to peroxide and the order with respect to potassium iodide, M and N, for hydrogen peroxide and potassium iodide. Okay. And then once you know the order, then you can figure out the rate constant. And then rearrange solve for K using any of the 3 trials. Okay. One challenge for you guys on this may be just actually setting up your formulas within Excel. Okay. In general, if once you've created your formula and then you highlight it and drag on down so that it does the same thing for the rest of the intervals, you can check one of those intervals and see, does that make sense? Does that make, or is it some crazy number? Okay, and see that you transposed your formula all the way down the column for all your intervals. Okay, and in general, once you do your scatter plot, okay, it should be just like the sample data that I sort of tried to describe. It should have a downward slope. The concentration of your hydrogen peroxide is going down. Okay. Okay, guys, that's it. Have fun. Bye.